Okay, so let's resume this nice day. So for the next presentation, we welcome Jean-Michel Loubès, who will speak about again fairness, but from a different angle. Jean-Michel. Oh, well, I think you people are coming. We can start in really 30 seconds.
Okay, so welcome to this afternoon. First, I'm very happy to be here to present this work, so thank you for this organization of this nice workshop. So nowadays, artificial intelligence, or let's say machine learning algorithm, are deployed for a large number of applications in insurance, in banking, and this belongs to the high-risk system. So that means that you need to pay attention to regulation. You add sectorial regulation, like for instance, the European Banking Association. You add privacy like GDPR. And now you have this new set of regulation from the European AI Act that goes just above, beyond all this previous regulation. So today, I'm going to take the point of view of the people who wants to audit, to inspect an algorithm, but also to the point of view of the people who want to be prepared for such an inspection, and trying to see what are the real challenge when you want to assess algorithmic compliance with respect mainly to bias. I could have chosen the other point of view, which is robustness. So I agree with Isabelle that we need to define the quantity we're using. For me, the definition is not my definition, it's the ISO norm that say that the bias is an information that influences a decision systematically. And then we'll see the impact. The impact is given by law. Maybe it's good, maybe it's unfair. Maybe you want it, maybe you don't want. And robustness is the ability to maintain the performance of the algorithm in any foreseeable condition. So just to give an example which are well known, so you all know this famous example of fraud detection of credit scoring, where you just try to make your best, you maximize your accuracy, you want to forecast in a very high accuracy, and what happens is that for people who look similar, that means they have very similar characteristics, the decision is different. So here, you see two people that have similar characteristics, but one is granted a loan and the other is denied. The only thing that changed is that there is a variable which is binary, and in my talk, it's not only binary, but in my talk, for sake of simplicity, I will talk with binary variable. So for me, there exists a sensitive variable which is 0 for the minority and 1 for the majority. And here the majority is men and the minority is women, for which there is a bias towards rejecting loan for women. So this happens for tabular data. You have other example for text data. This is a very interesting example that we worked through with Bordeaux Hospital. In fact, you can use LLM to monitor verbatim from the emergency. People go to the emergency, want to be attended, and then they describe their symptoms. And they use some LLM and then train. And you can see that if you just take exactly the same one, but you just change the gender, the pain score for women is minimized. It's not the common saying that women are more resistant to pain. It's exactly the opposite, because data is biased, and for years, male doctors have received women and saying these women express too much pain, let's lower. And here you have a bias because it's systematically underestimating the pain score for women, and that results in the fact that women are treated less quickly than men with this kind of algorithm. And then you can have also image. So here we use, we generate an image of banking inspection, and then we use VGG to try to label correctly. And as you see, you have an algorithm that gives very interesting labels. So here it's both sexist and racist. So it's perfect bias. Then you can also use VGG19 to try to forward some kind of characteristic. And here you have an expert, and the woman is called bossy. So here it's really biased in the sense that you have an external variable that influences the decision. So this is quite now almost common sense that algorithms in machine learning are biased. And in fact, we've been working for almost 10 years, both at INRIA and in research chair in ANIT in order to tackle this issue. So just to explain our motivation first, what we want to really define what is bias and try to build measure of bias. And then measure of bias taking into account the uncertainty of the data. And then once we had this measure of bias, then we wanted to mitigate the bias. And mitigated by the bias, you all know that you can just cure the data, or you can just train better during in-process modification or post-process the data. And then at the end, we try to explain a little where this bias comes from, and we try to build some causality with some counterfactual. And so I'm from probability, so I used a lot of optimal transport, but not as Arthur says. But then when I joined INRIA, I joined a team which is called Regalia, because it means regulation of AI. So people came to us to present real data set. We had people from regulation authorities like NIL, Cour des Comptes, Perrin. We had also some local authorities, like some cities. We had data, and they came to us to say, can we use this? Are we compliant with respect to previous regulation, moral regulation, or the new artificial regulation? We had some banks, we had some human resources. And then we discovered that all this work was not useless, it was a necessary step. But what we really needed to inspect real life was to develop new tools to inspect. And to do that, we needed people that know norms, that know what is legal compliance, both sectorial but also from the EU Act. And we also try to understand why do we have bias and where this bias come from. And to do that, we needed multidisciplinarity research team. So we tried to gather people from different fields, from optimization, from law, from aero optimization, from machine learning, also from privacy, to be able to solve this issue of how to inspect an algorithm, a real-life algorithm, and how to provide proof of compliance with respect to these notions. So I skip away explainability, I skip away privacy, which is also at the core of our research, and just here try to focus on bias. So first you need to read the AI Act, and you need people to read for you, as I'm a mathematician, so you need legal experts to try to decipher where there is bias. So here you see, it's just an example, you have lots of articles, but in the certain article, there are these two notions that tells you that first, you have to pay attention to the group of persons, and you must really try to understand the impact of the decision, and this is closely related to the notion of statistical parity. So you have to measure this influence, but you have also to try to look at the errors and errors in a moving environment. So this is not well defined, but they say you have to really, for any known or foreseeable circumstances. And this is key point. That means that if you just train your data, and you have your training data or your test data, and you say, okay, I'm done, maybe it's not enough. So if you want to assess compliance with respect to bias, you now, for decades, you have a set of measures that are mainly related to notion of independence between a variable and what I call the behavior of the algorithm. Behavior of the algorithm we discussed with Michele yesterday. For me, it may be the algorithm or the loss of the algorithm. So the algorithm, I will call it y hat, and the loss for me it's L. So it's the loss between y, the reality, and y hat, what I measure. So the measure, if you look at these traditional well-known measures in bias analysis, you can divide in three main types. The first one are related to the variability with respect to the mean behavior. So you look at the expectation of the algorithm and you condition with respect to A. So if you have just an algorithm that's doing classification, you just recover the famous or infamous disparate impact. If you just want to measure the variability of the loss, then you just the mean, and you have this famous equality of odds criterion. You can change it and use whatever your statistical background, if you like information theory, if you like covariance, if you like Erdos, I don't know, the HGR. You have lots of generalization of that. Maybe you want something which is not only the mean, but which is the world distribution. So here it's related to how the distribution change, distribution of the algorithm, or distribution of the loss. Or maybe you want to dig into causality, and you can try to do a thing. But all these measures have something in common. It's that if you want to measure them, they really depend on the distribution of the data. So my talk will be sort of in a way very similar to Toon's talk today. So if you want to inspect an algorithm, it's in a way very similar to what people do when they're trying to look at food security. If you want to look at the food security of, let's say, a yogurt, you want to look at bacteria. So you have the product and you want to inspect it. Bacteria is the in vivo version of the bias, which is the in silico version of the bacteria that hides into your lines of code of your algorithm. When you want to see if a yogurt is good, you want to inspect the whole system that processes the yogurt, then first you look at the raw material. It's built on living matter. It's exactly what you do when you do machine learning, because you start with living matter, which is the learning data. Then, if you want to look at the presence of bacteria in the yogurt, you see how all this was processed. And maybe there is some issue in the whole process line, and it's exactly what you could do. And it's the famous bias amplification to see if the bias was added by the algorithm. And then, at the end, when you want to look at the yogurt, you have to ask people to give them, and maybe the storage is bad, maybe the way you transport the yogurt is bad, or maybe the way you're going to look at the yogurt as bacteria in itself. And that's exactly the bias that could be induced by the testing data distribution, the testing data distribution that is used to compute this bias measure. So if you're an inspector inside a company or an external auditor and you ask to test the compliance with respect to bias of a machine learning algorithm, what are you going to do? So first, you're going to, you know that the algorithm is meant to work on a world. So there is a distribution, unknown. That is a distribution of the data on which the algorithm is deployed. So this is unknown. Maybe they don't want to give you. So ask the platform. For instance, I made a test for the European Commission for Amazon companies. So we ask Amazon to provide us a sample of their customer, or it was the buy box algorithm. So they gave us just a sample. So we ask the platform or the person who is inspected to give us a distribution on which we're going to conduct the test. So what do we ask? We ask the distribution to be similar, and we want them to be loyal. Are they able first to provide us a distribution which really conveys all the distribution of the data? So we conducted some experiments. So we use a huge test sample, and we divide it into 100 subsamples. So each dot here corresponds to a computation of the accuracy of the algorithm and a fairness measure, which is equality of opportunity. So if it's 0, it's fair. And then we add these 6 algorithms, and then the 4 here at the bottom, which are a corrected version of some of them. Corrected version with adding some penalty to enforce equality of opportunity. So what you notice first that this biased, unfair model behave correctly with respect to accuracy. But if you want to inspect the fairness, it's basically unfair. But if you were given this one, this subsample, you will say it's fair. So you really need to be, there is so much variability here that if you don't take into account the variability, providing one subsample is not enough. So you are really to design a method of experiment to really be able to assess, to prove a compliance. And then you see that when you try to repair the algorithm by setting some penalty, then optimization, as you said, is not very good, because here you enforce equal opportunity, so it's more centered around 0, but you destroy accuracy. So you gain one compliance with respect to fairness, you lose compliance with respect to robustness. So even if you're willing to give a true representative subsample, it's difficult. What happens if your platform, let's say X, and you're in a way disloyal? What does it mean to be disloyal? It means that you want to cheat, you want to hide your bias, and in the sense, you want to manipulate the data. So you're going to give an empirical distribution, manipulated, in the sense that first, the data looks similar, but is unfair. Looks similar, that means you have to choose a distance, and you have to be able to prove that the distance between your true data sample is very small with respect to the distribution you use to test. And then you have to be compliant in the sense that you have to have your fairness measure lower than a certain threshold. If you look at most global measure of fairness, that can be expressed as the expectancy of one function. It's not one-dimensional, it's multidimensional, but it's like that. So are there theorems that enable to compute fake distribution, that enable to manipulate this kind? So the answer is yes. If you choose, for instance, distance which is Kullback-Leibniz distance, then there is a way to prove that if you want to find the distribution which is as close as possible to the empirical, but that satisfy a fairness constraint, there is a solution. In this case, it's a unique solution. This solution is only a re-rating distribution of the true one, and the way it can be computed very easily. The only thing you have to do is to minimize this quantity, which is convex. So you put a gradient, and it's almost immediately. So in fact, what you recover a distribution which has a given stress level, and this is the difference between what you observe on the data and the thing that you recalibrate. It's very close to what people do in survey sampling when they do calibration techniques. Of course, you can change. So it's good because it's feasible. It's not good in the sense that you just reweight your sample. If you want to create new observation, you can almost solve something similar using optimal transport. You change the distance. You don't want the distance to be Kullback-Leibniz. You choose Wasserstein distance, which is the Monch-Kantorowicz distance that you use in optimal transport. And here, again, you can prove that for a weakened version of this constraint, you have a solution. And this solution, you just have to minimize this. So sometimes it's tricky, sometimes it's easy. And then you can have new observation. So the takeaway message is that if you give me a fairness constraint expressed in a mean, I can design a new distribution, or just by reweighting or creating new observation that look very, very similar by choosing the distance, any distance I put 2 examples, but that look alike the true distribution, but that the fairness which is fair. So I can give you the illusion of fairness by a subsample. So this, for instance, to give you some example, it's something very versatile because I can also test robustness in the sense that I can just push away some distribution. I'm not entitled to do only fairness, but I can put any constraint in this kind. I can look at the stability. You can do other things than fairness with these theorems. So, what does it mean? It means if you want to study compliance and the property of a system, you have first to stress it. You have to look not only at what you see, but you have to put it under stress. And this is well known. If you do sports, when you go for the doctors and the doctor want to know if your heart is fit after a certain age, if you want to do competition, you have to undergo this kind, and people put you under a stress test. You all know, people who work on banks, that there are, from the European Banking Commission, you have stress tests for banking, which are not normal conditions. So my first message is that if you want to look at the robustness or the bias, you have to take into account that it's not only the data you have trained your model on or the data you think it's the reality, but you really need to put this stress test. So I give you some example. I'm going to show you some simulation where we just simulate some data set with a control level of fairness. And the fairness, I choose statistical parity from 0.2 to 0.8. What we're going to do, we're going to subsample and to evaluate fairness, and then we're going to do this manipulation. So we have different type of manipulation. We can, as I said, choose entropy, Kullback-Leibniz or Wasserstein, and then even when you try to create, maybe you just want to change only the labels. That means the decision and the sensitive attribute, or you want to create really new fake individuals. So you have different ways of doing that. So in these 2 plots, so we compute at each time 1 sample, and the subsample which are here are just here in green and here in brown are the variability induced by the sampling. And then we just manipulate the data with different methodology. And here you have the mean of each data. So for each data, we compute a manipulated data set. And of course, what we're going to monitor, because the manipulated data set is fair in the sense that this disparity impact is equal to 0.8, what we're going to monitor is the distance between the original sample and the manipulated data set. So what you see first that if you start with fair data set, the distance is small. And of course, the more bias you have in your original data set, the less distance you have with respect to your fair data set. That means here, it's easy to see that this is not really this one. But what you can see is that up to a certain level, when you do test, that means up to 0.52 and 0.6 with Wasserstein, you can completely fake fairness. You fake the 0.8 disparate impact fairness with your unfair data set. That means this is for someone who wants to assess the compliance of an algorithm, it's difficult because if you have someone who's working in an adversarial way, he's going to cheat completely on the compliance. And as a regulation authority, or even if you are head inspector of a bank in a third line of defense, and if you cannot trust a model you have bought, or is in another filial, it's very difficult because then the regulation authority is going to go after you. I can show you what you can do. This is the adult data set. And you see, so 0.3 is a disparate impact in the original data set. And we can manipulate this data set with this kind of Wasserstein manipulation. We can really fake fairness. We can just have a disparate impact to 0.8 with a very small Wasserstein distance. So basically, if I'm allowed to pick a representative sample, and if the representative is only a distance with respect to a true, I can give you exactly the illusion of fairness, the illusion of compliance. It's only data manipulation. So this is complicated if you use this kind of global measures. So if there is a very nice technical report by lots of co-authors from Berkeley that's called Towards Guarantee of Safe AR that explain that if you really want to inspect an AR algorithm, you really have to work with norms, that's true. But you cannot do that without what they call a world model. What is a world model? It's either a collection of data distribution or some causal generative process that you control. And this is really needed to compute all your measurements according to the world model. That's really the spirit of what people do in banking regulation, where they have this kind of world model. They design what could happen to the data, and then they just assess their compliance with respect to this world model. If you can deploy your algorithm either on real world or on what is called sandbox in the regulation, here you can also monitor how your algorithm will impact the data, and you can use this feedback to enrich your world model. So this is not, maybe this is not static. This is meant to react to the decision. But without this world model, it will be very difficult to prove any compliance. How to design the world model is something that it can be numerical twins, it can be closed sandbox, you can imagine it can be assumption you have, it can be regulation, it can come from ethics consideration, whatever, but you need this thing in order to compute your measure. Otherwise, people like us will be able to manipulate the data and make you believe whatever they want. So this is maybe a kind of negative result with some positive guidelines. Now I want to just switch a little. What can you do specifically on bias? When you do bias, you know that there is bias in the data. And you know that if you put bias in the data, then you'll have bias in the algorithm. So this is the infamous adult data set, which is well known. So you know, for instance, that you have very few rich Caucasian in your data set. So if you compute the disparate impact, it will be around 0.6 with some variability to quantify the uncertainty. And if you build your algorithm, you have disparate impact, which are quite similar. If you make tests to prove if the bias is at the same level, it will tell you yes, it's the same bias. So here you put bias in the data, the bias in the algorithm. It's the same distribution, so it's just the effect of the algorithm. So basically, you just learn an information from the data. Sometimes it's very different. Here, we have exactly the same beginning of the story. You know, you have few female which are rich. But when you compute the disparate impact, so it's 0.3, here's the starting point of the bias in the data. For many algorithms, the disparate impact is lower. And if you make your test with this algorithm, they will tell you that you have amplified the discrimination. That means that the algorithm, for the same data distribution, made things worse. So you have this bias amplification effect. So just to have some positive, of course, you can post-treat your data and you can increase your fairness, but here you don't know what you do. But here, this exists, but here today, I just want to see, was it possible to understand why this bias amplification phenomenon occurs, and could we have foreseen that this bias amplification will happen? So this is very important, because if you want to prove the compliance of the algorithm, here it's easier because it's the same distribution and you just isolate the extra effect of your algorithm, whatever the data distribution. So this bias amplification, it's something which is well known. Here I give you another example. It's a work with L'Oréal, where we want to make beauty recommendation. And when you do beauty recommendation, there is one important variable, it's called L, which measures the darkness of the skin. And if you see, this is the disparate impact to forecast that someone is attractive, or it's a high level of beauty, and you see that the data is biased. That means that for small value of L, that means for darker people, you have less, the odds to be recommended attractive is much smaller, as if you are white skin. If you're too white, it drops, but there is an area, but for dark. And what is very important here, you have this bias amplification. That means that when you train your algorithm, then your algorithm is not answering the question who's the most beautiful, but as it's the title of a very nice paper, it's just answering the question who's the whitest. And here you see, so mirror, mirror on the wall, who's the whitest among all, is just the AI interpretation of the famous Snow White saying. So here you see you have clearly a bias amplification of this effect. So this is something I claim that you could have foreseen and you could have treated. So I'm going to explain, to try to give you a new explanation of why machine learning algorithms amplify bias in the data. So I didn't know the level of maths of people in the room, just to recall what is machine learning. Machine learning is about minimizing a loss. So you have a loss, which is the sum of loss for all individuals, and you have a model which is parameterized by parameters here I call theta, and what you want to minimize. And you have a lot of optimizer, and one of the most common is gradient descent. So gradient descent, that means when you want to minimize this, you just move your parameter trying to go to the lowest point. So here I had a nice animation, but in PDF, I tried to make the animation in PDF. So you see, I start with my three little balls here, and then you see the gradient descent, and you see the descent, and it depends on the seed, and then so sometimes you don't reach. So basically, when you try to solve this, your algorithm try to find the solution of the gradient of L is equal to 0. That's what you do when you do machine learning, basically. Recall, I have a setting where I have a minority and a majority. So I could divide my loss into the individuals that belong to the minority and the individuals that belong to the majority. So this loss I call L0, and the other I call L1. So when I train, I try to minimize these two quantities. I could have built a model only for the minority or only for the majority, but maybe I'm not allowed to because I cannot make difference. Maybe I don't even know the source of bias. So what I'm solving gradient of L equal to 0. So if you recall that L is L1 plus L0, I'm solving this equation. I could have solved something not with a full data model, but only using the majority. If I solve the model with the majority, I find a minimum, which is theta hat 1, which corresponds to this. And what we claim is that the bias amplification when you use this gradient descent comes from the fact that in some cases, so the difference in the model is only, we're not solving this equal to 0, but this equal to this quantity. We're just claiming that in some cases, this quantity is small in a certain sense, and it's just a perturbation of the majority-based model. So for us, I'm going to try to prove you that this bias amplification comes from the fact that you gradient descent completely disregard all the minority part of the data. So I knew Kantorovich theory because I was doing optimal transport, and in France we call it Monge-Kantorovich theorem. And then we discovered that there was, in optimization, Newton-Kantorovich theorems about the theory of perturbation that tells you the following thing. If you want the difference between a solution f theta equal to 0 and f theta equal p theta, when under some assumption, p theta is so small that it makes little difference. What are the assumptions? The first assumption tells you that there is little variability of the variability. It's expressed using the maximal eigenvalues of the Jacobian matrix of the perturbation. So this is supposed to be small. And on the other hand, you have lots of variability of the true one if you remove the perturbation. That means that you have the minimum eigenvalue of the Jacobian of this corresponds to F1, which is small, which is large. So if you are in this solution, in this condition, when you try to solve this equation, basically the two solutions are close. The solution without perturbations, we call it star, and the solution with the perturbations, they close. They closed, they are in a radius which depends on tau divided by delta. It's something where you measure the largest perturbation of the minority and the smallest perturbation of the majority. So if you have something where the majority is very, very variable and a high variability of the majority, this will be small. And when you learn, it will be very, very difficult to distinguish between the solution using all the data and the solution where you use only the majority. So if we apply this theorem with some modification to the learning problem, then you can explain a little more in the sense that what is bias? Bias in this sense is disregarding completely one part of the data that corresponds to the minority. And what is bias amplification? It's designing a model only with the majority that does not take into account the information conveyed by the minority. In mathematical terms, we say that here, when we learn our model, it's very close from what we call the stereotype solution. And the stereotype solution, this radius depends on this quantity. And this quantity is here the maximal variability of the Hessian of the minority loss divided by the minority, the smallest variability, the various eigenvalues of the Hessian of the majority. So this is, in fact, a new bias measure which relies on the model you use, and it's very focused on gradient descent. So if this happens, you know that you're going to be very close to the stereotype. Here you can have, so this proof here is quite geometrical because it relies on Newton-Kantorowicz. If you are in a simple version where you have only the regression case, in the regression case it's easy because it will depend on the eigenvalues of the covariance matrix. If you have the covariance matrix which is split into the minority and the majority, so you just have this which is S0 plus S1 with just a rescaling factor, and you can make all the calculation or apply the theorems, and the quantity which is analogous is the maximum of N0 S0 and 1 S1. So this is a phenomena which is also, it happens when you have unbalanced data set, unbalanced either with respect to N0 or N1 or the eigenvalues of the covariance. So you have two phenomena that place, the number of observations and the variability of what you learn. So one first conclusion is, if you have something which is unbalanced, either with respect to the population size ratio or with the variability ratio that can be measured with the new bias measure we provide, what will happen? You will learn only the majority behavior. And if the models are far, then of course you will just apply. You think you learn the data, but you learn only the majority. And of course, you will amplify the bias. We can, so that's why we call it when majority rules, minority lose. You can do a little more, which is this nice figure. So this is a simulation in the case where you have multiple extra local minima. So basically, this is what we want. We want to converge to minimums which are inside the red balls. So we start everywhere, and what happens is that when you try to minimize the gradient is always in very, 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 in fact, in all the white part of my set, the gradient of the majority of all the data is completely aligned with the gradient of the majority. So when you compute this scalar product, it's positive. So when you minimize one, you minimize the other one. So you try to learn your model, but you favor the majority. And only in these small balls, this one, you encounter zones where you favor not the majority, but the minority. That means that if you train, you first have to train and to reach this area, and you know that the solution of this area are small. That's my first theorem. The first theorem tells you that this is small because here you have the theta hat 1, that means the solution for the majority, and the true is also on the ball on the opposite. So what happens, you travel first to this ball, and then you have to enter this, and only at the end you do something that favor the minority. So if you're very unlucky, you're never going to cross these balls. So your model will result to the bias amplification. And because remember, these balls are can be very small if the difference is small. You can go a little further because you can imagine trajectory that first train only the majority. So you travel to the majority theta 1. And then you ask yourself, can I go to the true one? And what we can say that it's like a quantum space. You go quite fast to the majority, but when you want to move inside the little balls, it will cost you a lot of iteration. Because it's very, very difficult to move away from these points. If you think you have the gradient is combination, L1 is 0, and then the other is very small. So to get away from this trap, from the trap of the majority, it will cost you a lot of time, a lot of GPU if you train heavily. So, but if you want to learn your minority, you have to. Otherwise, you're going to amplify. And in this way, we can quantify the minimum amount of time which is necessary to get away from this solution. And of course, this is small, so this is large, so it costs you a lot of time to get away from this trap. But we can compute this a measure, which is a kind of minimal training time. You have to train your model in order to be not sure, but at last necessary to reach a zone where you will learn something about the minority. This is a difficult theorem. Of course, if you are in the case of the regression, then you can look at the dynamical system, which is the path of the gradient. You can make all the computation. You have the closed form solution of the path. Here you can have results which are easier to prove. How does it work? So this is what happens. So what I plot here is the loss for the famous adult of the majority in green, the complete. In yellow, it's the majority, and L0 is this one. In order to have L0 not too small, we rescale by the number of parameters. And what you see is that, in fact, here, you train, and training the complete data and the majority, it's almost equivalent, and very quickly you have. And basically, everyone stops in this thing because nothing moves. But if you really want to learn well also your minority, you really have to force your model to almost multiply by 4 the number of epochs in your data. And here you see that the test loss. So you quickly achieve a good level of accuracy for the model, general model in mean, and for the minority. And you have to train a lot longer to train something for the minority. And in this case, you have no bias amplification, but for the solution. Before this work, I never waited so much time to have this. So basically, here, that's the fairness over cost you can have. So Toon was saying this morning, fairness is not about optimization. Here, what we claim is that if you want to learn the behavior of the minority, I'm not claiming I'm solving the fairness, because if the data is unfair, it's still unfair. But to learn the level of unfairness of the data, it has a lot to do with optimization, because you have to properly optimize your model. This was done for this. You can, here it's another example. I cannot tell you the industrial, but the task is, let's say, to try to determine how to throw a balloon on bridges. so it's expensive balloons, so you have to be really able to recognize, to make the difference between a road and a river. And what happens is that for some, so we had very nice recognition between roads and rivers, and for some particular images, there was a bias due to the fact that either it was close to the sea or because it was rainy. We discovered that there was a bias which depends on the level of blue in the histogram. You can understand, because if your model try to think that something which is very straight is a road, if the gray is bluish, it looks like a river. So basically here you had a bias with a 23% of error. And if you want to throw a very expensive balloon, 23% is very critical. And here you see you have exactly the same type of phenomenon. When you train, you really monitor, and if you only monitor this thing, to reach the same level of accuracy, you really have to train a lot longer. So if 90% is your level of accuracy, then you have to train long time enough to reach this level for everyone. Otherwise, it's this bias amplification effect. Here the bias amplification is about the loss, and in the additive was about the forecast. You can have this kind of techniques. We had also for ResNet in image classification. So I think it's time for me to conclude. What we have three messages. The first message is that you have my first message. If you want to prove things about compliance, you need a world model. You need extra assumption from human, from legal requirement, whatever. But if you want to understand how bias is processed by the algorithm, then you have to pay attention to the optimization. Not optimizer are equal. I show you gradient, but there are other optimizers that are better than other. And this is very important because otherwise you will not all the information, but you will only learn the majority information contained in the data. And what is nice is that if you try to pay attention to the way you optimize, you will reach the same level of bias in the data. You will not amplify. To do that, you must know what you're looking for. Because at the beginning, here, we had no idea of this bluish effect because there were no variable called bluish in the data. So if you know, you can monitor your loss and you can compute your L0 or L1. If you don't know, it's more complicated, and then it's other stories when you try to split maybe your loss into adequate subgroups. And that's all. I think I'm going to stay here.
I was wondering, how do you define, like, what's the majority, what's the minority? Is there any kind of limit?
The minority is the one which is not. So first, if I want to prove compliance, I just look for the regulation authorities that explain to me maybe I think there are 28 variables in the French law that can induce regulation. that can induce discrimination. But if I'm using economic variables, so maybe self-preferencing in the case of the Amazon. So what is minority? Minority does not matter for me. It's just imposed by the regulator. Today I just take the point of view of the pure mathematician that obey to the regulator and want to help authorities or people to be prepared to an inspection. So but here from the optimizing point of view, here the minority is clear. It's the one for which has the smallest eigenvalues of the Hessian, and for which this ratio is the smallest.
We can take one last.
I have several questions, but I take just one. Can I sum up by saying that you just need to train for longer? And is there a trick, or just need to wait longer? Because the learning rate is slowly decreasing. So eventually, do you need to restart the learning rate? Do you need to change something during the training? Resample the data, upsample the minority? I don't know.
The trick is that if I want to be sure, I just train first. I train for the majority, and then I reach this because I'm sure that I reach this small ball, and then I train for the whole model very long time, sufficiently with respect to this lower bound. What, sorry?
But do you change something because
first
you
I
don't know what's the minority. So in the end,
to
apply without knowing what's the minority, do you just train longer and hope it's going to work better?
I know what is the majority and minority because first I know what I want to protect from.
Yeah.
So
you know, but I mean, if I want to apply it, and maybe I have a more complex setup where I have more than binary biases, how do I extend it to a real-world application? Is my question, sorry.
Okay, so I don't have the answer right now because we're just working on that, how to split this loss in order to have a kind of domino effect where you learn tasks one after the other.
But the insight seems to be just train longer, it should be better. And
if you don't choose your for the gradient, yes, longer is better, and it depends and you have to enter these balls. So to enter the small balls, you have to choose a good a good starting point. So the good start and the trick is first, if you train the majority, then you're going to reach these balls.
Okay, because I was checking, I couldn't find the right paper, but I think it was Llama 2, where they really realized that most of people training LLMs were not training long enough, and they really reached a higher standard by training for so much longer. So
the solution will be first with normal optimizer, train longer, and then design specific optimizer to get rid of this bias issue. Okay. This is work in progress.
Thank you very much. Thank you. Thank you again. Okay, so next speaker, Evgeny? Okay, Evgeny Jain. So next speaker is Evgeny Jain. So we'll talk about optimization approach.
Right, so hear me? Yeah. So thanks for having me. I'll finish the presentation of Jean-Michel first and then start mine. Okay. Right. This morning I realized that my presentation is extremely technical. It doesn't have any pictures. Then I heard the presentation of Jean-Michel. I was, okay, nice, there is some math, and but my math will be less sophisticated than that of Jean-Michel, so let's see. I actually won't really talk about fairness that much. I'll present an approach to multi-class classification problems and a certain framework where you can add more or less any type of constraints and post-process whatever you want and have some statistical guarantee. So I'm a statistician. My kind of only job and joy in life is to prove some theorems related to generalizations and things like that. Yeah, so since it will be relatively technical, but I will try to be as pedagogical as I can. The main message is that there will be general framework, some examples, where you can put a bunch of different constraints that you like, that are formulated in a certain form. And for any problem of this type, there is one kind of optimization algorithm with guarantees, the statistical guarantees that come with. So I will, from now on, those who are not interested in math part, you can stop listening. Yeah, so at the beginning I will give a quick introduction into randomized algorithms, randomized classifiers. So it will be similar to what Isabelle was talking about. Then I will provide several examples of different type of constraints that you might want or not want, so that literally not my job to decide which constraints you want, but I will give some examples. Then all of this will be formulated in a unifying framework from like linear optimization perspective, and then there will be an algorithm and things like this. So it will be eventually it will get technical. Okay, I will start with the problem of multi-class classification, and I'll put myself in the supervised learning framework. So bear with me. So I'll have all this notation will be throughout the talk. So I'll have x, y. X is a feature vector. Will be living in its own space X, so think of it as being some vector. There will be a label, and so it's a multi-class classification problem. So I'll have a label that takes capital K values, could be binary, whatever you want. A standard notation will be pk of x. So this is just given an individual, what's the probability that that individual will have a label equal to k? If k is binary, what's the probability that that individual is going to get a credit or whatever? And so the important object would be a prediction function. So usually we think of prediction function as something that eats like an x, like an individual, and spits you a number from 1 to k. So here it will not spit a number, it will spit a distribution on this number. So that's the randomized classifiers. So this delta of whatever I put inside, it's a distribution on whatever I put inside. So in this case, I put capital K different objects. So delta of capital K. It's just the distribution on k elements. And my prediction, it will be a random variable. So we are used to y hat. Here I will formalize it slightly more. So y hat is a prediction so that when I condition on an x, so when I see an individual, it's distributed according to that kernel pi. And there is just an extra assumption that's very important. That essentially, an assumption tells you that we are not cheating. If I observe an individual, my prediction is independent from the true label, because if it's not, then there is sort of a data leakage, so that assumption is very reasonable. And so in the classical problem, at least when you open any book on statistical learning, you start with something like this. You try to minimize a risk which is equal to the probability that the true label differs from your prediction. Overall prediction functions, for example, you could do it over all prediction kernels. In this case, the answer is classically known. It's what you predict is the most likely label. So it's extremely intuitive result. Still requires a proof, but the result is very intuitive. So given an x, what is the most likely label? This most likely label you're going to predict, right? So even though you're optimizing over randomized classifiers, the answer is non-randomized. So that's just a theorem that tells you this. All right, so this is the setup mainly to introduce the prediction kernel. Sometimes you might want to add additional constraints coming from whatever ideas you might have. So in this case, I'm adding an extra sign, which is R, which is a rejection. Imagine that I would like to make a classification, but sometimes I would like to say, well, I don't know, or I prefer not to predict. And then it's up to you to treat whatever you want to do with that data, right? So in this case, I will introduce an A hat. So my A hat, it will be sort of an action. So I'm allowing myself to not only output the classes 1 to k, I'm allowing myself to output other objects. So in particular, in this case, I just added one extra atom into my distribution. And so a possible goal, so that's not the only goal, but a possible goal could be that I would like to minimize the probability that my prediction differs from the truth whenever I'm not rejecting, whenever I'm actually issuing the classification, under the constraint that the probability of rejection is at most alpha. You know, let's say alpha is 5%, and I would like a classifier that classifies as accurately, but 5% of the time tells me I don't know, and well, it's up to you to do whatever you want to do. You know, you take a more sophisticated model to process like 5% you pay to ChatGPT or whatever. And so a first observation is actually once you formulate this problem in terms of prediction kernels, it becomes a linear program. So linear program is something that requires that object to be linear in pi. If it doesn't make sense to you, don't worry, but it's an observation. So this is a linear program under linear constraints, right? That observation is going to be with us throughout the talk. And there's also a description of the optimal prediction function. So we can just theoretically, assuming that we know all the distributions and everything, just write down what is the optimal prediction function, right? So in this case, it's going to be of that form. So if the probability, if the largest probability of y given x is not large enough, so that individual is very uncertain, then you'd reject. Then there is not enough certainty in the problem, so I prefer to reject. And if it is certain enough, then I would put that prediction, right? It's very, very simple. What is important is that there is this threshold, and that threshold is something that you do not know beforehand. This is not alpha, this is something that should satisfy certain equations, and it depends on the distribution that, well, essentially you have to estimate this threshold. That was also happening in the Isabelle's talks. All right. One observation is that, so that result holds on a certain mathematical assumption. So it's not for free, it just stated like this, it's not true. If there is certain assumption that holds, then this is true. Here's another assumption that, well, another type of constraints that you might be more interested in this workshop. So right now I'm splitting my x into whatever feature that is nominally non-sensitive and whatever you decided to call sensitive. And right now I'm just issuing the usual prediction. So everything is the same, but let's say I would like to add this demographic parity type of constraint, saying that the prediction should be independent from the sensitive attribute. Right? I think almost everyone mentioned this constraint. A way to formulate a relaxed version of this would be the following. Let me look at the probability that I'm predicting a given label y conditionally on a given group. Let me compare it to the just probability of giving that label overall. If all these numbers are equal to 0 for all y and all s, then we just know that my prediction isn't dependent from the sensitive attribute. Right? Generally, you might want to relax it with some values and things like that. So first observation, this is also a linear program, again in the space of these randomized predictions, and under certain continuity assumptions that are actually way more complicated than in the previous example. You can write down what's P star, and it will be again deterministic. Since write down, it will be a certain type of thresholding as usual, where threshold is unknown, you need to estimate it, and things like this. So I think that type of results appeared in very many different papers under different flavors. And my final example is about the set-valued predictions. So imagine I'm doing again the same thing. I'm in multi-class classification problem, but instead of producing one label or a distribution on labels, I would like to output a subset of labels. Right? So hopefully that subset is not too large and it captures whatever the true label actually is. You can also formulate it in this sort of form, but slightly differently. Right now, for each individual label, I'm going to assign its own kernel. So my kernel right now is thought as a vector, p1 to k, and the pi is valued in 0, 1. Right? So then what I'm going to take, I'm going to essentially, for each k, I'm going to flip a coin with respect to this pk. And if the coin lands on 1, then I'm including that label into my set. Right? So that's how I'm going to define, given any functions of this form, I'm going to define this random variable that is set valued. Right? All right. So what you could potentially want, you could potentially say that, okay, let me minimize the probability that, not the only way, but let me minimize the probability that my true label is not inside. So I would like to be as accurate as possible, but I also do not want to have large outputs. So in expectation, I do not want to have more than, let's say, b equal to two labels. Right? Sometimes it could be more, sometimes it could be less, but in average, I don't want to produce too large of a set. Right? So funny enough, so first of all, it's also a linear program. It's also a linear program. It's not completely obvious when you look at this, but once you write, it's also a linear program. And under, again, certain continuity assumptions, you can prove that the only thing you need to do is consider deterministic gamma. So deterministic gamma, the only thing it means that this pk is either 0 or 1, like just nothing else. It's not valued in between 0 and 1. And the optimal will be that include all those that are large enough. So look at each label for the probability of each label for every individual, and include all those labels that are sufficiently likely to happen. Right? This threshold is, again, something that you do not know a priori. It depends on the distribution, but you can effectively estimate it. Right? And so the theme here is that all of these different constraints, they actually generate different subcommunities, and people study them theoretically, practically, and things like this. But there is a very, very common theme. It's always a linear program, as long as you're ready to relax it to randomized classifiers. It will always admit a deterministic solution. There will always be some continuity assumption. Okay. So final thing, depending on what are your objectives, you might want a combination of different constraints. You might want to add equal odds and things like this. And as Jean-Michel said, many of these constraints will be written as an expectation functions. So you typically always can put it in this framework. Okay, so my general setup will be the following. So all that was just to motivate a general setup of the problem. So I will have some prediction kernels that will be valued. So I'll have some action space. So my action space could be only the labels and the rejection. It could be all this set valued map. So it's something that it's up to you to decide. Depending on the application, you typically can specify it. And I have some distribution on top of it. So my prediction kernel, it's an individual and spits my distribution on my action space. So all these lines are exactly the same. I will have some risk measure, and my risk measure will be written in this form. So for an individual S, for an individual X, what is the fit of the prediction I had? And then I'm taking the expectation. Here I need to be careful because my previous risks were not written in this form. My previous risks did not have to do almost anything with X. They were Y. The point is that both are equivalent, but in this framework, I'm not assuming this function little r is known beforehand. You might have to estimate it. It might depend on other things, and typically you're able to estimate it relatively efficiently. And I will have some kind of constraint. So for an individual X, I give a prediction A, and it measures the cost, the J's cost of me issuing that prediction. I'm taking the expectation. Right? And so the type of problems what I want to solve, I would like an algorithm, is kind of some guarantees, that tries to mimic the performance of pi star, which minimizes the risk under a bunch of constraints. Right? So it could be the constraints that I've presented, or maybe eventually we'll come up with your own. All right. So this is not a new problem. So statisticians knew about this problem a long time ago. Yeah, okay, so I decided to add an extra slide explaining. So if you don't want to listen, from now it will become more technical. So if you don't want to listen, that's the type of problem that I'm treating. There will be eventually an algorithm, so I will build it up. There will be statistical guarantees, and it seemed to work. And now I'm going to do some hopefully pedagogical presentation of math results. So at the beginning, I will assume that the R and C are known as functions, right? This is not true in almost any application. At least one of them is unknown at most of any applications. Right? But at the beginning, it would be interesting to answer this question: what can we do if R is known, C is known, but the only thing that is unknown is that expectation? What can be said? Then eventually I will relax it. I will say that, well, let's say R is unknown and C is unknown, and I have some estimators of them. And typically these estimators will come from your any favorite algorithm. This is why it's called post-processing, because eventually what I'm going to be post-processing is R hat and C hat. Right? So many problems can be formulated in this form. And then I will present some numerical results, which are very shameful, but there will be a couple of pictures that are not very informative, but I'll still show them. All right. So as I said, this problem is not new. There are very old results, like So here I'm citing 51, but essentially you can treat it with what people call in statistical literature generalized Neyman-Pearson lemma. So maybe if you remember your stat course at the very beginning, you studied the Neyman-Pearson lemma, which gives you an optimal test in a certain situation. But actually, Neyman-Pearson lemma is just a statement about linear programs. Like it's rarely taught as such, but it is just a statement about a certain very concrete linear program. And once you understand this, you can generalize it. And that's more or less what's done in this paper of Danzig and Wald. And actually, even Neyman and Pearson did it in more general form than we use it right now. And once you understand that it's a statement about linear program, you know something about optimization, you know that all linear programs, they admit some kind of a dual, and maybe it makes sense to look what's going on in the dual. And once you realize that, you essentially proven the generalized Neyman-Pearson lemma. On that, you should trust me. Like this, you write the dual. It's not the linear dual. It's more of a Lagrange type of a dual. It's, let's say, more for experts. The message here is that if I solve some kind of optimization problem of this form, so I have some function of lambda. Lambda is the Lagrange multipliers. If I manage to solve this, then under some continuity assumption, so it's a maximization problem. This is concave function. So everything is relatively feasible as long as you're able to compute gradients and things like that. Then there is a sort of a primal dual link that once you solve this problem, then the optimal sort of classifier, in this generalized sense, is given as a pointwise argmin of all of whatever that's sitting inside of this minimum, but with lambda being the solution to that problem. Again, this is only true under some continuity assumption. Generally, it's not. It doesn't have to be the case. All right. So this is a theoretical result, but it has some algorithmic implications to the extent that many papers been written in that type of framework, and I myself wrote also some papers of using that sort of ideas. Algorithmic application could be the following. Again, we are assuming this R and C are known, so what you could try to do, well, there is an expectation, and so far I assume that's the only thing that I don't know. Well, I have the data. If I have the data, look, I only need unlabeled data because I only need access. I replace expectation with averages. That gives me some new function f hat. I'm going to minimize it, and I'm going to do a plug-in type of algorithm. So that's the bread and butter of statistics, replacing stars by heads. And that's what I'm going to do. And doing that path, I think more or less I wrote my PhD thesis doing only that. All right. However, there are some issues. Like if you want to do some statistics, in a sense you want to prove some theorems and things like this, there are potentially some issues with that approach. Some of them are issues of sort of elegance, and other more fundamental, like numerical. So first of all this, as I said, relies on some kind of continuity assumption. And often case, already Neyman-Pearson, I think, people might know that the answer is non-randomized if you have a continuous likelihood ratio. If you don't have a continuous likelihood ratio, then you need to randomize. Same type of phenomena happens here, but it's already sort of a multidimensional problem, and putting a continuity assumption in this multidimensional problem can be tricky. If you don't have continuity assumption, which you typically don't because you want to kind of make an algorithm that doesn't rely on many assumptions, you introduce some tricks, you add some small noise here and there, and that is completely meaningless, but it makes the theory work. This is more algorithmic point of view, that function is concave, so it's nice. But it's non-smooth because it's a sum of minimums, so it's a sum of some kind of kinky functions like this. And once you minimizing, well, okay, it's concave, but well, minus it is a convex, so let's think of it as minimizing the convex functions. Once you're minimizing a convex function that is very kinky, it won't be very fast. It doesn't have to be very fast because, well, it's non-smooth function. You have access only to the subgradient, and you don't have curvature that would kind of drive you into the minimum quickly. So that's a more like stability computational issue. And the third issue is from the statistical analysis. It often goes through an assumption that, Jean-Michel said that gradient is equal to 0. Well, once your function becomes kinky, you don't talk about gradients, you talk about what's called subdifferentials. You want to say that the 0 belongs to the subdifferential. You write this down, and from there you write all the statistics in 5 pages. But and then you ask yourself, can you actually in practice write this down? Like if you're not ready to take lambda hat equal to argmax, can you write down that 0 in the subdifferential? And typically it's not, because if you imagine a function, just an absolute value, and you're making a subgradient descent, in order to be 0, you just need to luckily end up at 0. Everywhere else, your subgradient will be minus 1 or 1. Sorry if it's not very clear. Yeah, so that condition is nearly impossible to satisfy. And then comes another issue, that once you stop knowing R and Cj, which is often the case, combining all this procedure with unknown R and Cj, it becomes a bit of a pain. Like it's possible, but it becomes trickier and trickier with every step. Like at the moment you decide, okay, let me not make something purely theoretical, but something that could work, it gets trickier and trickier with every step. So we would like to kind of avoid it. And the key inspiration comes from this paper of Nesterov on smoothing. So Nesterov's message was very simple. Like if you have a convex function that is non-smooth, but you know how it looks, you can smooth it. It's very sounds stupid, but it's kind of that's what we're going to do essentially. You have a non-smooth function. Let's smooth it. What's non-smooth? So in the how do I go back? Yeah. So here non-smoothness comes because I'm computing the minimum. In machine learning, what we really like to do is take in they call it cross entropy. Well, cross entropy is sort of a smoothing of a maximum. So it's a soft max. If you have a soft max, probably you have a soft mean that exactly minus soft max. You do precisely that. There is deeper theory involved to this, related actually to what Jean-Michel was presenting about this duality in the Kullback-Leibniz divergence. But more or less, the idea is very, very simple. Replace minimum by soft minimum and hope that it will work. Soft minimum will have a parameter, so there is this temperature parameter that you always need to choose, and people in practice know that many do it. We would like to choose it somehow from theory-driven once for all and never touched. Once you're doing this, you obtain a randomized predictor. You lose deterministic predictions just immediately, because more or less this is why you're doing cross entropy. It's rarely just 1 and everywhere 0. It's more diffuse. Same thing. And there is certain expression for the prediction, randomized prediction, once you do all this replacement. You also gain many properties. You remain concave, which is nice, but you gain smoothness of the gradient. The gradient of that function becomes Lipschitz. And it's smoother with the temperature. So if you're in the very low temperature regime, your pies will be concentrated on Diracs. In a very high temperature, they will be diffuse. So the more they diffuse, the easier it is to do optimization. Right? But yeah, so you're losing the determinism. Okay. What is also interesting that once you build that type of function, this function, there is a certain quantity that you can associate to this function, and if you control it, you actually control in one shot both risk and the constraint violation. Surprisingly, it's not the functional gap. It's not f of beta, lambda hat minus f of beta lambda star. It's the gradient, which is actually a relatively strange thing because it's a convex problem, and in convex problems, we typically can prove much more than just stationarity, even though they're equivalent. But we do not often use that type of criteria of our success, because we can just do much more. It's in non-convex problems you can't prove much more than just gradient equal to 0 or goes to 0. And so the proposition is like this. That essentially is the control, is your violation of of constraints. Right? So if the gradient, if that quantity is equal just to 0, then you don't violate constraints. If that quantity is equal to 0 and your temperature is it's 1 over temperature, so beta is 1 over temperature, so temperature is very low, then essentially this pi beta lambda, which introduced through this exponential formula, just coincides with the optimum in terms of risk, not in terms of the expression. All right, and so it asks a question: how to find a lambda with a small gradient? That's not as obvious as it might seem. At least for me, at the beginning, I thought, well, that should be easy. I mean, it's convex optimization. Life should be simple. Not quite. Yeah, so we would like to minimize this function with an expectation. Okay, instead of expectation, what you can do, you can write stochastic gradient descent. So you always can find some kind of an unbiased gradient of that function. I'm not even going to replace this expectation by expectation hat. I'm just going to think about stochastic optimization. I'm not going to do forgot the word. Anyways. And in order to estimate the stochastic gradient of that object, the only thing you need to do, give me one unlabeled data, erase that guy, compute this. That's a stochastic gradient. It's very easy to see because once I put the expectation here, it becomes just the gradient of that. It's a stochastic gradient. If you know R and you know C, very easy to compute. Only needs unlabeled data. You don't need any other type of data. Well, the lie here is, of course, from the fact that you don't know R and C, but we will see later what can be done. And now the question that you have a stochastic optimization problem, and you would like to find an approximate solution to the minimization of f or maximization of f, so that the expected norm of the gradient is small. That's quite different problem from the classical convex optimization. And you want it to be very fast. So there are some subtle moments is that function is nice, but I would like my temperature to be low because I want to be as close to the optimum as possible. But if my temperature is low, then it will damage my optimization performance because my function becomes less smooth. So there is a certain trade-off, and you actually would like to develop an algorithm for that objective and not for the functional gap. All right. Well, that can be done, but not by us. It's still surprising that the algorithm that actually does the job was published in 2019. Seems to be an old problem optimization, but in the convex case, there are certain subtle moments which makes this problem difficult because you kind of wish to have very, very fast rate of convergence. If you don't, then just do gradient descent. But if you want very fast rate of convergence, then you need to be smarter about what you're doing. And the algorithm is called SGD3. It was initially proposed by Alan Zhu, but published later than that paper, and then analyzed a bit by Foster et al. And more or less using their algorithm, plugging it in and working the mass out, you can prove that if you give me capital N unlabeled data samples, these capital N unlabeled data samples, they just correspond to the amount of gradient evaluations. How many times you're allowing me to evaluate the stochastic gradient. Then you have these two guarantees. The first one tells me how much I'm violating the constraint. It's 1 over n, but it's a square, so actually it's 1 over root n if you raise the square. And the risk guarantee that I produce the lambda hat. When I do the plugin, then the expected risk of whatever I produce is at most the best risk I can achieve, plus the 1 over root n. But this n is the unlabeled data, so it's not that data hungry, let's say. There are certainly some things that I'm hiding. In the sense, there are some constants that are problem dependent and things like that. But there is a nice thing out of it that the temperature is very low. So temperature is 1 over beta. So you need beta to be equal to n. Yes, you will be diffuse. You will produce randomized classifiers. But they will not be too diffuse. They will actually be quite concentrated. If you are actually very diffuse, then it more corresponds to outliers than to the general behavior. All right. So that story when R and C is known, when R and C is unknown, you do a bunch of triangle inequalities, and you arrive to that theorem that build me estimators of R and C. Typically, it will be some machine learning models that you're already using. For example, one that predicts just probability. Just imagine in the context of fairness, one of them could be given an X, it tries to predict whether it's not good, but that's optimal. But given an X, one model will try to predict whether it's a male or a female. Your constraints will depend. Your CJ will depend on that kind of thing. So you replace by C hat, and in the risk it will depend on that type of quantities, on probability of Y equal to a label, to a given label for an individual, and that you build your whatever favorite model you want that outputs probabilities. You replace stars by hats, and that's what you do. And so the result says that essentially give me any estimators of C and R, and you just pay them. Like if you estimate R well, then that's small. If you estimate C well, then this is small. If for some reason you know C completely, which is the case for some application, then this is 0. Things like that. Right? Maybe it's probably time for my amazing experiment. Yeah, so we did some experiments in the case of regression, and you will tell me, okay, but what kind of regression? You're talking about multi-class classification. But okay, regression from multi-class classification, there is not like a huge difference. You just do very small beans, and you create a lot of classes, and you try to solve this problem as if it was a multi-class classification problem. That's pretty much what we're doing. So your risk is of this form, and you would like a constraint that f does not depend on the sensitive attribute. So I have an x, some sensitive, an x, which is some feature, no CV, whatever, some s, which is the sensitive attribute. I do not allow s inside of f. Because once you allow s inside of f, then there is all this beautiful theory of optimal transport. We know many things. When you don't, we actually don't know that much. There are some approaches to that problem. I'm not sure we understand deeply what's going on. There are some nice papers that explain that there can be issues in the case of classification, but like theoretically, we don't. That problem is not very well understood, but we can still try to make algorithms about it. And there is another algorithm that we compare to. There is the package FairLearn, which used to be at Microsoft, and right now I think it's independent. And there is a paper of Agarwal, Dudik, and Wu, where they propose some kind of in-processing algorithms where we reduce this problem to a sequence of cost-sensitive classification. Weirdly enough, it's not implemented in the FairLearn because they only do classification and not regression. And yes, so we compared. Since we are doing post-processing, there is some kind of a base classifier which is very unfair but sort of very accurate. And then, well, this is all the curves that we saw today: unfairness, risk, blah blah. I'm not sure what kind of conclusion I should draw from this, but it performs not too worse, but maybe not much better. But it's different algorithm. It's a post-processing algorithm. So if you don't want to change whatever horrible monster you have in your in your pipeline, then we'll just add an extra bit to make it more horrible. In processing would be just erase whatever you're doing and put our new thing. Yeah, and okay, so that picture is probably completely useless, but kind of fun to look at. Is that once you draw distributions, so I have 4 sensitive attributes. I'm solving regression problem, and I can forget about any fairness and draw the distribution of predictions. Well, it looks something like this. And then you can try to do this post-processing without S. So S is not used. It's not quite the transport. It's some kind of a different transport. Then, well, they become closer. So I don't promise them to be the same. Yeah, just to wrap up. Sorry for. I hope it was not too bad. Understandable. But yeah, I think a message would be that if you're able to write down your constraint in a linear program and your risk as some linear functional, then you can pretty much use this framework, and it comes with guarantees and relies only on convex optimization. So it's quite a simple plug and play version, and typically estimating risk and constraint is more or less obvious because you write them down and you see what kind of pieces you need of distribution to substitute. And from those who are more interested in theory, I find it quite quite interesting that it's an example of a convex problem where you would like to control a norm of a gradient. Which still, when I say it doesn't make that much sense to me, because you can prove much more. You can prove like a gap in functionality or distance to the optimum. But here it's literally about the norm of the gradient, which I find cute, and it seems to work. All right, thank you.
Thank you very much. And you did it great, so don't worry about that. Any question?
Thank you. So I had a small question because when you have your bounds with the big O and so on, I didn't see where you have the number of classes. Is it somewhere hidden in the capital O?
Yeah, it is.
Okay.
It's root of k.
Okay.
Here it's all. Well, actually, it's a. In the paper, it will be quite hidden but discussed, but because there is a norm of certain matrix that is involved, and this norm of this matrix will scale as the root of the number of classes and eventually the log of the number of constraints.
Okay.
So in classes, it will be root, which is bad if you have a lot of classes, but in constraints, it will be, yeah, it will be log.
Okay. And also the proportion of people in different classes, should it be like uniform, or if you have extremely rare
so
classes?
this whole thing is hidden here.
It's in here, okay.
So it and here you substitute whatever type of bound you wish.
Okay.
Because this is all unlabeled, so we don't care. Like that's how problem formulated. Okay, so problem is formulated. Minimize my expectations, and I can sample you IID axis. There is no y anymore. Y or groups are hidden all in your ability to estimate that quantity. So if you have very small groups, you will not be able to estimate this part.
Okay, makes sense.
Yeah, so thank you very much for the presentation. I have one question. So if I understand correctly here, the C for the constraints, we do not use label. So it means that the separation and the sufficiency related fairness metrics are not applicable, or is it a little bit hidden somewhere?
Completely hidden.
Okay.
It's a good question because okay. As I said, so in this form you can put whatever you want. It can depend on y or not. But once you write like this, you need to work around with your constraints. You need to essentially the only thing you need to do is to write that expectation is equal to the expectation of conditional expectation. Like this, you get everything depends only on x. Certain quantities will appear. You will not know them. And for example, you do separation or whatever you want. Here it will depend on, let's say, probability of an x being a female, which by default you don't know. So in order to know C, you would have to estimate these probabilities and substitute them.
Okay, I see. So for separation, I can see for the tower property, but for the sufficiency, it seems more complicated since
sufficiency is what again?
It's just that you switch between your y and y hat. So it means that instead of having conditional to your y, it's conditional to your y hat. And it seems that in this particular case, this seems a little bit complicated.
Yeah, I think it will not work here. Because to me, calibration is sort of a risk in itself. Like it's not a constraint. Like you. Because it is related to calibration, right? So you essentially want calibration, but then why would you put your problem in this framework? You would put more. I know there are millions of papers that discuss, I don't know, multi-calibration and things like that. So but it will not. I think it will not pop up here. Like maybe in binary case it will, but certainly not in the case of regression, or maybe I need to think about it.
Okay.
But stand in assumption that it doesn't work.
Okay, thank you very much. I have maybe one small question. Towards the end, when you test it out with 4 classes, it's 4 classes, right? For the numerical.
It's a 4
experiment.
sensitive attributes. It's
Oh, it's
regression,
4,
but
okay.
4 sensitive attributes.
Oh, okay. So
Yeah. So the
So-
y
so-
is real valued.
yeah, okay.
No, y. No, it's some kind of classification. I don't.
Yeah.
Maybe it's even binary classification. To be honest, that I don't remember.
Oh, okay, okay.
I know that there are 4 sensitive attributes, but maybe it's just a binary classification. It's possible.
Yeah, because my question was related to why are you using quadratic risk when you are in the multi-class? But
Yeah, no, it's a good point you're asking, because but first of all, I think it's a typo. I think it's literally regression problem. So it's not, there is no k.
okay,
It's r.
Okay.
I think it's communities in crime. There is something continuous to predict. I don't know what, but there is something continuous you can predict, and you split it in something like pairs of race gender, and there are sort of 2 races, 2 genders in this data set, and that creates you 4 sensitive attribute. But it's a regression problem. It's a typo.
okay, I see. Thank you.
One last question.
So thank you for the presentation. It was really scientific and makes one feel more intelligent. So if I want to apply it to real world problems, what would you suggest? What libraries? What let's say I have some transformer model, and I think I have bias, but not really observing it. How can I apply your methodology?
I don't know.
Okay.
I mean,
How did you do? You mentioned
write down
Microsoft library. Sorry, you mentioned the Microsoft library.
yeah, but okay, but transformers, with transformers, I don't know what you predict, because I mean there is kind of self-attention, so you predict
multi-label
itself.
usually. Usually. you
Okay,
predict
but if it's
multi-label.
multi-label, then okay. First of all, there is no library that does this, mainly because I'm lazy. But generally speaking, it's very easy to implement.
Okay.
It's extremely easy to implement. You
Take SGT3.
You sample one data point. You take a gradient of soft mean, which is computed by backprop in a second, and you make, okay, it's a SGD3, so it's a slightly different algorithm that is used. It's not quite just gradient descent, but it's not very far from gradient descent with, I don't know, let's say, adaptive regularization. So you need to add some with weight decay. Well, yeah, in neural net they use the word weight decay. So it's kind of gradient descent with some weight decay,
Okay.
where the weight decay parameter also increases eventually. But I don't see much problems to use it on whatever you want, to be honest. Just need to compute gradients and do backpropagation.
Okay.
And then substitute things. Yeah. So then eventually what you will do, you will compute the lambda, because you do the gradient descent on lambda. You compute it, and you substitute it right here. That will be your lambda, and it will give you a new probability. So you had before some kind of softmax output, and right now it will be a new softmax output. So it will give a new probability.
Okay, so PyTorch should be enough. Is that all? Is that
Oh,
you
for
meant?
sure, for sure,
Yeah,
for
okay.
sure. I know. There is nothing fancy here. It's just convex optimization.
Looks fancy.
No, there's literally nothing fancy. Like, it's just convex optimization.
Thank you very much. We are out of time, so sorry. So you see, you did well, because there was a lot of question, and I also get that there's a call for some kind of help to implement that. So for transformers. So thank you. It would be nice. Thank you very much. Thank you. Thank you again. And now another presentation. So now letting the floor to Michele Loy. Just introducing your topics. Thank you very much.
Okay, thank you. Does it work? Okay. So, nice to meet you. I am a senior scientific manager at Algorithm Watch, and it's an NGO working in algorithms. I'm also a independent consultant in AI ethics, and also adjunct professor at University of Milan in AI ethics, though the later is not larger part of what I do. This is a paper that it's coming out from my latest turn in research, where I was still working mostly as a researcher in, no? Okay. In academia, with latest turn of this research, after starting a chain of different investigations with Marcello Di Bello, who is a scholar who isn't coming originally from the field of AI at all. He worked, wrote his PhD thesis at MIT on the use of statistics in criminal trials. And Nicolò, whom I met in Milan, where I still live, who is a PhD in statistics, and we've been doing quite a lot of work at the intersection between statistics and ethics. And this latest turn of research that so far has produced 2 papers, only one of which is public, also because the other one we just wrote it very fast and submitted it, and will be this one. So the first paper took like 3 years to write, I think, and it signified for me moving away from papers you may have come across from me otherwise that were firmly within, I think, a dominant framework that tries to test fairness or find criteria for fairness by looking at consequences. I think that all of the approaches that we've seen here are empirical, and especially the statistical approaches, the non-causal, the first wave of group fairness measure, for instance, they're purely observational. They're just looking at distributions and not asking why do these come about. Then clearly there was a significant innovation with Kushner and others of including causality. Basically, we want to deal with the difference between something being explained by, let's say, gender or sex as a variable in the pure statistical sense. And this is something I think that very often gets misunderstood, especially when people outside of statistics hear this, say, oh yes, and the different probability is explained by gender. Then people think it's explained in a causal sense. But when statisticians are speaking, actually, most of the time, you cannot make this inference. It's only saying that if you compare the probability, it's different. This is not what explain means in common language. And at a certain point, the debate evolved to that point, and causal models were introduced, modeled typically by using Pearl or equivalent formalizations. And so we had this causal wave of understanding of fairness. And we first wrote this paper that is basically trying to find a discriminant criterion between unfair and fair processes in the language of causality, using Pearl, the do calculus, so we really are concerned with the idea that an intervention on the counterfactual, so of course you cannot change, for instance, a person's gender in reality, or sex, it's harder to change, maybe you can change. But anyway, that's not what we mean in the counterfactual, right? We are not imagining someone going to a transition. We are imagining someone who retains most of their properties except those that are causally influenced by being a person of a certain group. Or it could be race, as the US people say, or ethnic group, and so on, which also causes a lot of problems. As we were working with this paper, there were some cases that emerged that are especially difficult to explain. I think cases that no one in the AI This is not a philosopher looking outside of this debate would think about, because these cases originate mostly from this thinking about the fair trials situation. What makes a trial, like a criminal trial, fair or unfair? What kind of evidence can we use there? And these basically are cases where one element that seems to play a role is this idea of spatiotemporal specificity, which led here mostly Niccolò and Marcello to write this paper very fast. And this is mostly dealing with, if we are right, this will be the Columbus egg of statistics, because it really seems that there is a gap between the probability that attaches to events described in a general way and the probability that attaches to a specific event in whatever conceptualization of probability you would have. So very often people seem to be making this inference from probabilities of generic events, like, there is a higher probability that someone with certain features, we call them X, makes a crime, or maybe a specific type of crime, and the probability that this person here has made a crime in this place would attach to some sort of evidence, and so on. Now, this talk will become paper 3. I don't want to fully attribute it to my co-authors, not because they don't deserve, but mostly because we haven't discussed all details yet. So I don't know how much they share what they're going to say. So don't quote them about this, unless to say, oh, they had some very interesting idea. So again, the starting point is that the main families of fairness criteria that we discussed here not only conflict with each other, but they also don't seem able to explain some more subtle distinction that, if you are like me, you will think exist. So just as a quick summary, with statistical parity, calibration, and quality of opportunity, the group fairness metrics, we are only looking at basically how we observe the world to be. With causal fairness, we are actually requiring, so in the first ones, we are requiring some sort of parity in some sort of observational statistics. In the second one, we are requiring that a certain feature, for instance, being a man, has no causal influence on the outcome, or we want to reduce this causal influence. And none of this helps us to explain this puzzle or paradox, if you want. The puzzle is this. Consider these two cases of statistical evidence. In the first one, John is suspected, or is suspected more than someone else, to have committed a crime because John belongs to a demographic group, and if you look at the statistics, there is a difference in the propensity or in the probability that someone from that group commits the crime compared to the general population or to the other groups. This type of evidence has been discussed a lot, and I think intuitively creates a lot of problems. Surely the judges have not felt comfortable with using this type of evidence. And there's even a case where a judge in the US, this type of reasoning has been overturned in the later stage of the trial. But then consider John, again, who is suspected because it matches a profile And someone with that profile has been witnessed to be near to the crime scene. Now, notice that the second case has a lot of things in common with the first. For one thing, it creates an inequality of opportunity in the sense of the statistical group metric. So if, for instance, the profile says that an Asian man has been seen near to the crime scene, then the false using this evidence probably creates an inequality between the false positive. So the probability of an innocent Asian to be convicted becomes higher than the probability of an innocent non-Asian. And the probability of an Asian, of a man to be convicted becomes higher than the probability of a woman to be convicted, even though innocent. And yet, if you are like me, you will not think that in spite of creating some measure of inequality in the false positive rate, using the second type of evidence is as problematic as the first. And surely the courts don't think this. Now, what type of answer can we give to this type of puzzle? My intuition has been to go back to something that felt outside of the first causal paper that's connected with causality. And then if someone at the end wants to ask in relation to Chiappa, to path-dependent conceptual fairness, I'm happy to go in details. So remember, in causal fairness, we try to differentiate, so we don't look just at the outcomes, but we want to differentiate based on the source. We don't want certain type of features to be responsible for the outcome in a causal sense. There is a version of this idea that you can find in philosophy, and actually from much earlier, there is a version of it discussed in a paper by Lipper Rasmussen, I think in the 90s, that basically says that it's not so much that a protected group is responsible for the outcome, but it's the fact that the prediction that we make is grounded or is a reflection of an unjust social structure. So this is much harder to model causally, even though the idea of an unjust social structure is clearly a causal construct. So for instance, then discusses this principle according to which statistical discrimination is wrong when those who benefit from it, so let's say, imagine a society that is divided in two classes, a very rich class exploiting a much poorer poor class. So these rich people benefit from the statistics because, you know, all favorable statistics, they pay lower premiums, whatever. And at the same time, they are, let's say, the rulers, so they're more powerful. So they are responsible for living in a society in which other people then have different sort of lives, which generate these statistics that are unfavorable to them. And then there is also this idea from Hellman, this is a more recent paper, this idea that statistical discrimination is wrong when it compounds prior injustice. So I'm drawing this idea that what actually, at least one element that has not been fully captured in the discussion of what contributes to unfair algorithms is this idea of reflecting injustice, like them. But these theories still don't explain the puzzle. Because, oh wait, let's remain here. Why they don't explain the puzzle? Because if you think about the case of the court, we will still probably consider like witness evidence to be more fair than the sort of statistical generalization about crime rate in different groups. Even both of them can fulfill this criteria for injustice. So even the witness evidence can be, so notice these are not meant to be applied, first of all, to that type of evidence. It's talking about statistical discrimination. So first of all, it's very difficult to apply them to that puzzle. And if you try, it's not easy to see how they can differentiate. So this presents a explanatory pathway account. This explanatory pathway is connected to the other paper, paper number 2, that tries to distinguish this different way in which we explain things when you're thinking about the general social event types versus particular events or more narrow events classes that are characterized in time and space. And the idea here is that having what we may call a direct causal mechanism, so something local in place, when we make a prediction, actually helps with fairness. So if you're more likely to have unfairness when your explanation, first of all, it's at a level involving large social structures. So, and here when I say explanation, I'm talking about the explanation why a certain feature is predictive. So you have this feature set X that you use to make a prediction, and you're asking yourself, how is it possible that these features in X help me predicting Y? So if this explanation, most of the time you don't have it, right? In insurance, you don't have to have it. An actuarial table contains no explanation. But you can try to say, okay, let's try to say something plausible. How is it possible that this statistically predicts this? So if the story that you give involves large social structure, most likely it's also to capture injustice, because a lot of the social structures we are unjust to some degree. And they remain more unjust when there is no displacement, and then I will clarify what I mean by that, by a more direct causal mechanism. So one of those causal mechanisms that is specific in time and place. So the key insight here is that we are trying to capture a moral distinction, not on the basis of the data, of biases in the data, not on the basis on the impact, but on the basis of the type of explanation you will need to provide if you want to explain how is it that a feature set like X can be predictive of Y. And it's grounded on this distinction, basically paper 2, between the generic one and the particular one, combined with this idea from Rasmussen and Hellman that when you have the generic explanation, so think about zip code. Why is it zip code allowing me to predict insurance risk of the many kind that you know? Well, most likely the explanation you can give has something to do with the society and some process in society that segregates people, or at least directs people who are from disadvantaged group to be more likely to live in certain area, which in the US is correlated with what they call race at the same time. By contrast, there are different types of direct causal link, and to get a picture of that, think about if you have seen 12 Angry Men, or any movie in which you get a jury discussing, okay, is the accused person to be convicted or acquitted? They are usually not talking about how likely are people in this group to make, based on general statistics, how differently likely are they to make a crime. But they're talking about a very specific crime, a very specific feature. So this is a different type of explanation. Why? Because the causal model behind it is a different kind of causal model. The first causal model, the one that would explain why can be predictive of insurance risk or of criminality, and so used in policing, has to do with these involving groups. And the second one has to do with more micro models of what's happening in certain places at certain time. So the key insight and of this hypothetical solution, again, this is really work in progress, even I would say work at the beginning, is that the evidence becomes less unfair when its explanatory relevance is not primarily mediated through unjust social structure, but instead through a direct causal mechanism specific to the case. So let's try to unpack this. The evidence, think about evidence like a woman is seen running with her bicycle, with a poker on the basket of the bicycle. Now, in the context that we used to call diagnostic in other papers, where we already have evidence there is a case, a woman has been killed in her house, the examination of how she's been killed is compatible with a woman being killed with the poker, and so on. Then we can say the fact that someone saw this woman running with her bicycle, let's say white woman running with a bicycle with a poker on the basket, this increases the probability that a certain and specific woman and a woman fitting that profile is guilty, because of a very local, specific causal model of the world. Clearly, this isn't saying that there is a sort of general propensity of women who drive bicycles to kill people, or even women who drive bicycles with pokers in their baskets. So, if you have something like a black woman near a crime scene, even though using this type of evidence may increase the rate of error against, say, a black woman, and even though this is I would say that's become almost paradigmatic of the disadvantaged category, because of certain context, this is not as problematic. So it's like this more local explanatory type of explanation, the fact that's available helps with fairness or decreases the unfairness. And notice that this is still true even if counterfactual fairness is not satisfied, because this is still compatible with, for instance, race as a social construct having a causal influence, so not just a correlation, but a causal influence on the probability of, say, a black woman passing with the bike. Maybe that's a black, it's a black neighborhood. Why is it a black neighborhood? If you try to model this causally, you will put something like a race feature in the Bayesian network. But in spite of that, this worries us much less. And our practice is on this local level explanation. Now, of course, we haven't been thinking about insurance very often in these conversations, even though I started thinking about locality in the context of a paper written for AXA that I cannot say more about because it's their paper. That was in the context of false, the fraud prediction, which has probably more in common as an insurance practice with this sort of, who is guilty of what than risk prediction. There is probably a bit more that we can say about even insurance premium. And For instance, we may think about the difference between charging, again, usual example, a neighborhood identified by zip codes or whatever, because of a statistical correlation where the where somehow the imagined explanation of this is that it's tracking social disadvantage, which raises risk. And the more case-specific evidence, for instance, charging higher premiums based on documented water damage to a specific property, which of course we can still aggregate and imagine algorithmically to be done for a lot of different houses. So it's not like in the case of jury that you can apply only to one. But it's more, if you think about the causal process there, it's much more local. We don't need really to think about what's happening outside of this causal model of a house with water coming in and ruining, I don't know, the foundations of whatever. And this is still true, at least if your intuition is like mine, this is still problematic, even if at the impact level, we can have inequality, because maybe there is a correlation between being a member of a disadvantaged group and living in a neighborhood in which there are a lot of houses with sort of water leakage. So it's not like we have to disinfect from the influence of the causal variable as in counterfactual fairness. Something else is going on. It's as if the availability of this modular causal package that can explain the relevance of, I don't know, water leakage sanitizes it, not completely, but at least partly. Because of course we can still have socially undesirable outcomes at the level of communities impacted, and we may worry that disadvantaged groups are more unfavorably impacted. But I think if we think in terms of procedural fairness, it feels less unfair than the first one. So we suppose that there's something more going on here. Of course, these intuitions, as always happens with philosophers, we rely on our intuition. Then one could test perhaps this empirically through survey and see if this intuition is widespread. I'm relying on the fact that this time of you will fit there is a bit of a difference there. Now, what will be the, how am I doing with time? Okay, that's, I think I'm on time. So, what are then the policy implications for predictive models? Well, in a sense, the guidance that can be given, unfortunately, is not as quantitative or scientific as someone said first. If this got really scientific because we got the maths. So this is not scientific in that sense, because it's much harder. So in terms of like broad rules or broad heuristics, the first thing will be that when you end up with a model that's using certain features, you need to think about a causal story behind it. So this is not a super big novelty. If you are endorsing causal fairness, counterfactual fairness, you already kind of be upfront about making causal hypotheses, even when we have very little evidence for them. The second aspect is that a heuristic is that you're kind of in a safer place if you use direct evidence, by which I mean this evidence that is related to more local causal models. And why? Because these more local causal models kind of see the ability to exist independently of these broader social phenomena that are responsible for other correlations that matter morally, arguably more than, and not just because of the impact. And then, again, on the basis of your causal story, why does X allow accurately, more or less, predicting of Y, to shy away from those features, those type of access? It can be even the combination of features, even if doesn't mean you have to look at features independently, where it kind of makes sense that what's behind the correlation is some problematic social structural injustice. This has some implications for algorithmic system. To some extent intuitive, maybe to some extent counterintuitive. So let's think about two areas. Policing, algorithms used in policing. It will imply that facial recognition is less problematic. I mean, if a bias in facial recognition would be less problematic than, say, predictive policing targeting neighborhoods based on demographics. Now, I don't know how much this intuition is shared. Also, at this point, remember something that I wanted to say. Don't attribute these views to Algorithm Watch. These are personal views. Let's not create problems. I'm talking here as independent scientist. Now, facial recognition, of course, has a lot of other problems connected to surveillance, power, and so on. But from the basis of this theory, there's sort of like having a bias in facial recognition, the famous gender shade things. It's kind of a less of a problem that, or at least it contains fewer moral problems than predictive policing targeting neighborhoods, because that really is this type of, scenario in which the relevance of the evidence being a neighborhood for the police action is mediated through this sort of broad social practice that probably include injustice, compared to someone specific being seen in a certain neighborhood and just using AI to automate that. And the other example, probably more relevant for this room, is that, for instance, insurance pricing using, we had the example of water before, or individual driving data, assuming that what makes them predictive has to do with the sort of causal model of people driving a car and not some weird social correlation. That will be preferable from credit scoring using zip codes, where we really don't see how the zip code themselves can increase the risk, except maybe in the case of earthquake risk or things like this. Another benefit is that it explains why socially salient traits matter more. We're not so concerned with discrimination against people who have the combinational feature foot 35 and liking crime movies on Netflix so much. And when we care about traits that are not socially salient, we care about, because what is socially salient? Socially salient, as defined by Liber Rasmussen, are traits that have an explanatory role across a wide range of contexts, often contexts that are not related one to the other. So the typical subsets, like gender or sex, depending on how you see it, or ethnic group, nationality in certain contexts, and so on. The more a society is shaped by these differences, the more these are socially salient. Why are these important? Not because they are protected groups legally, even though clearly this is not unconnected. I mean, ask yourself, why are they protected? But because typically when these categories or their proxies become predictive, it's because something of that sort, this sort of broad social structural problem is going on. And just now, as a take-home message, so the key theoretical contribution is that, we take already in the literature, also Lazar and Stone recently, very famous philosopher, Lazar especially, saying, well, not all departures from group parity are morally equal, and we should ask why and what's the role of injustice. But they say we should look at whether the people receiving like the worst treatment are more disadvantaged. And we're not saying that. And also like Hellman, we are not saying it's because it's like, basically it's a penalty on people who are already penalized. That's not the point. The point is how we end up explaining the predictive power that we exploit. And this has connections to insurance risk classification ethics, where we have had this question, like, can we distinguish the kind of features that have been work saying, okay, is the feature one that people are responsible for or lack? It provides an alternative to that theory. Legal evidence theory, as I said already. Algorithmic fairness metric, like this past specific and factual fairness, can has some relation to it. I can say more. And clearly the epistemology of statistical evidence, this will be paper 2, and this maybe new argument that we should care a lot about the difference between the probability of the generic event versus the probability of specific event. And the practical guidelines, now moving from the academia to the practitioners, are again that you should you should ask about the explanations for prediction. Correlation is not sufficient, statistical tests are not sufficient. You should ask why. Prioritize features for which you can give a plausible kind of local explanation, and avoid those where the only explanation you can give that's plausible has to do with these broader social structural things that are affected by injustice. So challenges and future work. Of course, we need to turn this into, if we want to turn this into an applicable approach, we need some empirical identification. How do we assess our theories about explanations, what explains, that's common problem with all causal approaches. And for a quantitative implementation also, we need probably to develop further mathematical frameworks to capture these ideas. So I hope that the idea is clear enough, and thank you for listening.
Thank you very much. As usual, any questions?
Thank you for your presentation. I'm not absolutely comfortable with this distinction between the individual history, I would say, and the statistical approach. And I would like to ask you a question on what, and a concrete example we had in France on insurance. Insurers used to, I would say, to refuse insurance, to refuse insurance to people who had cancers. So they had cancers, and so you had cancers, they recovered, but they didn't get the insurance because they had cancers 10 or 20 years ago, and so on. And if you apply your explanation path, I mean, the explanation path is really logical. I mean, you had cancer in your life, so there may be, I mean, there is a suspicion that your cancer is not, is still somewhere. And well, there has been a lot of discussion with in the place, and actually there is of course a social stance to take, to say, well, we have the right to be forgotten after a while. But I think in this process of discussion, statistics helped to clarify the thing, because with statistics you could see that after 10 or 15 years, and the residual risk of declaring a new cancer was approximately the same as the normal population. So this is just an example to say, you see, sometimes statistics can help to clarify or to make it more objective than the individual explanation path. How would you?
No, I think this helps clarifying a misunderstanding. It's not that in the more local causal processes you ignore statistics. And after all, even the deliberations about the fact that someone has been seen at a crime scene, you can formalize that in Bayesian terms, I think. It shouldn't be a problem. It's everything that we are considering here is an instance of statistical explanation. The problem is more, how do you explain the statistics? Now, does the process that explains why, in spite, it's a nice counterexample, first of all, so thank you for raising this. This seems to be a puzzling case, because in this case, the natural explanation will say higher risk, but then the statistics says, no, the risk is the same. But then we should ask, okay, why is the risk the same? Do you have an answer to that question? If that answer to that question does not involve some sort of social selection, advantage, broad pattern of injustice, we may just accept the statistics and say, well, actually, here there is nothing to explain. The statistics is not causing a difference, and probably our intuitive model of the disease was just not a good causal model, because the body has the ability to recover that is much higher than we would have thought had we not consulted the statistics. So we can just take our local causal model of how a body operates with cancer within a social settings with, let's say, public access to healthcare, and say, not because of some social injustice, but just, okay, we update our beliefs about the probabilities involved because statistics. I think that should be okay. I don't think that's a violation of the principle. It would have been a violation of the principle if you say that there is a difference, because if someone is white and wealthy, then this increases a lot, then they remain the same. While if this person is black and poor, then there is a huge difference. And in that case, that creates a problematic case, because I think we are trading off two objectives. One is that we don't want to penalize the white person with cancer with respect to the person who didn't have cancer. And the other one is that we don't want to treat unfairly the black compared to the white. Because in that case, this theory says it's problematic, because what explains this difference would be probably the type of healthcare to which they access. And there, if we consider fairness alone, probably we should then treat also treat the black probability as if it were equal to not having a cancer, or also treat the white affluent probability as if it was equal to have a cancer, or some middle value, because after all, it's all subject to a constraint requirement if it is insurance, of some sort of overall sustainability.
Thank you very much. We are a little bit behind our schedule, so we try to catch up with a break. A short question, perhaps the last one, really small one, if there is any. Yeah.
So I'll make it short. My question is, do you think it's for health insurance pricing, do you think, so basically usually it's just based on the age of the person to insure. Do you think it would be more fair from your perspective to use the medical health record for pricing rather than the age, which is actually a proxy and could be considered a bias somehow because it's not the actual cause of illness?
Other excellent question, because this allows kind of testing the framework in real life. So I think then you need to take age and then ask the following question about age. Is the correlation with age due to something like age discrimination processes, or is it due to age being an indicator of those other processes which are more biological? So just a coarse summary of these other things that you are comparing as an alternative. And sometimes then we'll have to deal how to do things when it's both. But let's assume first a simple framework. If it is the first, then you should not use age and use the more specific parameters also for fairness. If it is actually, if age is just a coarse indicator of biological fit, then from the point of fairness, you may just keep using age, though you may have an inaccuracy argument or an individual fairness aspect, a different type of argument to favor the specific indicator. But it wouldn't be inherently unfair to use age because the causal story basically is the same. And then you're just using a vague, imprecise summary of those other features, which may be difficult to collect.
Okay. Maybe an idea could be that health, so people who have healthy habits, maybe they are privileged, I know, but have more, are aging less quickly.
Yeah, I understand.
And in the end, it becomes slightly too coarse and not as causal as we would expect. So is it somehow something we could reject, saying that we know that gender is a sensitive variable, but maybe age is also a sensitive variable? And do you know if there are projects trying to remove such a coarse variable to force maybe insurers to use more accurate variables for health pricing actually?
Should I answer in a coffee break or publicly?
Yeah, maybe.
The answer is yes. We are doing it. There are players in the market. SCOR is one of them, but we are doing it just to use, for instance, actual health habit, just to find the correlation, not more than correlation, causality, instead of just. But it's just market habits. I would add just it's market habits. People are used to use age because in the past it was most commonly used, and we were not using model necessarily, and it worked pretty well. And now with just like the data collection, we start just to get more. But there's a lot of stuff that you can see on the market using, for instance, just physical activity practices instead of just like age.
Just very shortly, what this argument tells about the use of those indicators is that even if they may still create quite a lot of disparate impact, the fact that it's a causal story that would exist independently of the social inequality makes it more okay to use them. But that will also be true of age if the reason why age is predictive is just acts as a proxy of this biological variable.
So I invite you to continue, yes, during the short break. So we'll just shorten a little bit the break, so just to try to catch up our schedule. So let's take 10 minutes break. So if you just
thank you.
Having worked, and thank you very much. Yeah, thank you.